Okay, so on this video, again, I'm going to very briefly discuss dilation, but more in the abstract, just on regular figures defined in space based on the dimensions and not based on any kind of Cartesian plane. So, for example, let's say I had a right triangle, right, and its side lengths were, I don't know, 12 by 12 by 12 square root of 2 for its hypotenuse, which is approximately, no idea what that is, 12 square root of 2. 12 square root of 2. 16.97, we'll say. Okay? And we'll go ahead and use centimeters, because why not? So 12 centimeters, right? Now, let's say I dilated this guy by a scalar of 2. Okay, so now we're saying our scalar is 2. Well, we already know because k here is greater than 1, we know we're going to get larger, right? We're going to have an increase in area. Okay, and I mean, should be pretty obvious. It's going to get twice as large, so that means we're going to be 24 centimeters by 24 centimeters, right? And our hypotenuse is now going to become 24 square root of 2. Which in turn is about 33.94 centimeters. Okay, so if we look at what we get for the area, okay, so that's going to be 144 over 2. We know that's going to be 72 square units or 72 square centimeters, right? And because we dilated by a scalar larger than 1, we know we're going to end up with a larger area here, right? So 24 times 24, so 24 squared, 576. So the area of a triangle, of course, is base times height, so that would be 24 squared over 2, or 576 over 2. That, of course, is going to equal 288 centimeters squared. And we see that pattern happening again. If I divide 288 by 72, right, I'm going to have a 4 as my reduction factor, right? And 2 squared is 4. So we see that pattern there again. Okay. But all I did was multiply each dimension, right, by my scalar of 2. And that gave me my dilation. Okay, so now let's look at another example. What if we didn't dilate by a scalar greater than 1? What if we dilate by a scalar similar to what we saw in the last video, a scalar in between 0 and 1, so a fraction, right? So let's go ahead and do, let's say, 1/4. So I want k to be equal to 1/4. K, of course, will be less than 1, however, greater than 0. And of course, anytime we talk about k, we're talking about its magnitude. I always have students ask me, well, what if the scalar is negative? And it's like, it doesn't really change anything because a scalar is a value of magnitude. It's not a value of positive or negative. We don't care about direction, we'll say. Okay? Anyway, went off on a tangent. So we're dilating by a scalar of 1/4 or 0.25, right? So we know we're going to get smaller. And we're going to get significantly smaller, right? So 12 times 1/4 is 3. So that side becomes 3 centimeters. Likewise for this other leg here, which means my hypotenuse is now 3 square root of 2. So 3 square root of 2, again, no idea what that is off the top of my head. 4.24 centimeters about. Okay, now let's look at the change in area this time. Well, we know we're going to have 3 times 3, so base times height divided by 2, so that's going to be 4.5 square centimeters. Okay, and when we divvy this out, so 72 divided by 4.5, we're going to get 16, and we know 4 squared is 16. So that goes into the nature, right, of area. And again, we can get into that a lot more in depth, like in person. So if you want to go into that, obviously come and see me or ask me when you see me. But that pretty much does it for this video. Dilation, again, very simple concept. It's even simpler not on the Cartesian plane. just in the abstract like this. But we see the same relationship between a figure, its scalar, and the resulting figure from the dilation. So let me know if any of this lost you, or if you're curious to understand further the relationship between, the increase or reduction in area based on the scalar. Goodbye.